Hey, everybody. So we're going to finish up talking about moments and center of mass. And so this is the third video on this topic we've done. And our goal here is we've been trying to figure out a way to find the center of mass for a thin plate we call a lamina of some arbitrary shape, okay? And specifically one that has a constant density through the entire shape. So we've gone through a lot of work to build from point masses on a single line and to then point masses distributed through the plane and finding their center of mass. And last time we did a simple shape that was simply a function between a function and the x-axis on some interval. And so finally, we're going to look at the most general case here. We have two functions, f and g, and our lamina is the space in between them, enclosed by them on some interval, right, that I have here. We're not going to go through the whole derivation this time. We've taken done quite a bit of detail on the derivations that have gotten us here so far. It's very similar, and I encourage people to try that on their own. But for this part, I'm just going to present the results. They're pretty intuitively similar to what we are able to do in the previous videos, right? In the same way, just as a quick sketch of the idea, right? We would use that same strategy we used last time of splitting this shape up into little pieces, rectangles, whose centers of mass we can determine by the symmetry principle. And you do this for rectangles across the whole shape, right? And add each of them up, and then in the limit, add up the moments of each of these rectangles, excuse me, and then in the limit, you get the moment for the whole shape. So doing this, here's where we end up. The mass of this kind of shape can be given by the density, rho, times the area, which is just f of x minus g of x. All right, that's the height of each rectangle in each spot in the approximation, and then the limit we get to this. The moment with respect to the x-axis is equal to rho times the integral from a to b of 1/2 f of x squared minus g of x squared dx. And the moment with respect to the y-axis is given by rho times the integral from a to b of x times f of x minus g of x dx. Right, and these are pretty similar to the ones we came up in the previous video. The difference being, this is the most general form. You just take g to be the function 0, and you get the formulas we came up with in the preceding video. Okay, and with these definitions in mind, we get the center of mass, or centroid, is at x bar, y bar, where x bar is my over m, and y bar is mx over little m. And let's just look at how these work out, because if I take my over m, I get rho times the integral x f of x minus g of x dx divided by little m, which is rho times the integral from a to b of f of x minus g of x dx. These rho's are constant, and the denominator is simply the area of the shape. So sometimes we can write this as 1 over the area times the integral from a to b of x times f of x minus g of x dx. And in a similar way, we get, so this is our actually, I'll just write it here. X bar is equal to 1 over the area, A to B, x f of x minus g of x dx. And we can do a similar thing for y bar. We get rho times the integral from a to b of, let's see, this is 1/2 f of x squared minus g of x squared dx over rho times the area given by this integral. And again, the rows can cancel, and I'm left with 1 over the area times the integral in the numerator. I can also pull that 1/2 out, so either way is fine. I like to write it this way. Some people leave the 1/2 in the integral, f of x squared minus g of x squared dx. And so that's our y bar. So this gives us our 2 coordinates for the centroid. Okay. All right, so let's just finish this up with an example. All right, so these are our, let's grab these formulas for the next page. All right. Oops, I forgot to copy. Copy. Okay, so here's our formulas. Let's apply them to the following problem. We want to find the centroid for the region bounded by let's see, y equals x and y equals x squared. Okay, so I always like to start by drawing. These are pretty familiar functions. It's pretty easy to see that these 2 functions are going to intersect at 0, 0, and 1, 1. There's y equals x. And there is y equals x squared. Okay, so there's our graph. In case we're not clear, we can see which function's on top. I also like to make estimates of where my centroid might be. It's not entirely clear where it should be, but right, looks more or less where we pick the middle of the square one with vertices at 1, 1 and the origin 0, 1 and 1, 0. But it has to be below that line y equal x, maybe a little closer to the origin. It's not entirely clear. But it'll help us if we get a wildly wrong answer, right? If I got a point above the line, for instance, this would make it obvious that that can't be the case. All right, so let's go ahead and compute what we need. We need the area of this shape. So the area of this shape is given by the integral from 0 to 1 of x minus x squared dx. The antiderivative of x minus x squared, let's go up here, is 1/2 x squared minus 1/3 x cubed. We're evaluating from 0 to 1. This is going to be 1/2 minus 1/3, or 1/6. So there's our area. Hold on to that. We're going to need that for later. All right, now let's compute our 2 moments. So these, or the integrals for the centroid, they're not quite the moments anymore because we did that cancellation of density and all of that. So first I'm going to compute this integral for x bar. I need the integral from 0 to 1 of x times x minus x squared dx. This is the integral from 0 to 1, right? I'm just computing this integral here. This will be x squared minus x cubed dx. This is going to be 1/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 1. We get 1/3 minus 1/4, right? It evaluates to 0 on the other end, or this looks like 1/12. Okay, so that's that integral. And let's compute the other integral we're going to need. This is going to be from 0 to 1. Squaring both functions, we'll get x squared minus x to the 4th dx, which will be 1/3 x cubed minus 1/5 x to the 5th, evaluated from 0 to 1. 1/3 minus 1/5. That's going to be 2/15. Right, 5/15 minus 3/15 gives me 2/15. So now I can simply use my formulas. The coordinates of the centroid are x bar, given by 1 over the area. So if the area is 6, 1 over the area is just 6, times this integral here, right? And we computed that right here and got 1/12. So 6 times 1/12 is 1/2. And then y bar is going to be 1 over twice the area. So the area would be, twice the area would be 1/3. So 1 over twice the area would be 3. And then times 2/15. And that works out to be 2/5. So the coordinates of the centroid look to be 1/2 and 2/5. Okay, that's it for us. I encourage you to take a look at the derivations, see if you can come up with these formulas. They follow a pattern very similar to the ones in the 2 previous videos. And it's a very useful style of thinking to get used to, but I'll leave that to you. But then also we've come up with these nice formulas for our centroid at the end. And I also hope you notice I'm breaking them down into simple bits, right? There's kind of a lot going on in these formulas, but we can pull out each little piece and do them one at a time. All right, thanks everybody. I will see you next time.